Hi everyone, this is the last video on the topic of statically determinate frames, and it will be the solution to example 13 and 14. So as you guys can see, these problems start getting a little bit more complicated, especially with this last one. So we need to figure out a very systematic way to solve this without making mistakes and using all the ingredients from the structural concepts that we talked about, reactions, shear force, bending moment, and deflection, to make sure everything gives us the same answer and everything is consistent. So in this case, clearly, starting with a deflected shape will be a mistake. You're gonna take a little bit of time on understanding how this should bend. So let's leave that for the end. So let's start, for example, to calculate this reaction here on the right side, using this point as the pivot. So I know my moment will be 30 times 2, that's 60. Then the other one is 30 times 4, that's 120. And this one here, we have 12 times 6, 72, times 3. So we need to add all this up. So the moment caused by the UDL at point A is 216. So all these moments combined are equal to 396. That then if we divide by 6, we are going to get this reaction here, which is equal to 66. Now that we know that reaction is 66 and the total load is 72, that means this reaction here on point A is just 6. And finally, we can get the horizontal reaction straight away. We have two loads of 30 pushing the structure to the right. That means we're going to get the reaction here of 60. Okay, now let's think about the bending moment diagram straight away. We can see straight away that our column on the right side will not have any moment. So we can say, because the reaction is 0, the horizontal reaction is 0, and we know this has to start at 0. We don't have shear force, so that's 0 over there. We also know this point here has to be 0. And we also know we're going to start here at 0. The load of 60 causes tension on the right side, so the moment is going to go initially in this direction. So it's going to be 60 times 2 is going to be 120. So that's what we know so far. Then we have a couple of loads there. We have a UDL. So let's maybe do, again, the shear force diagram to make sure our bending moment diagram gets correctly done. So let's stop and think a little bit about this. In this case, we know this shear force here is 0. And then on the beam, we have 6 to start. Then we have a UDL that gets minus 72 all combined. So this goes as a straight line all the way to 66. And then the 66 closes the shear force diagram at 0. So this is all good. And then if we look at the other column, we have 60 in this direction that then get halved by the load of 30 and then get halved to 0, go back to 0. So we have 60 here and we have 30 here. Okay, so we're in the position to confirm this area is the 120 that we just used. But now we have another area, which is 30 times 2. So this one area is equal to 60. So our moment is 120 here, but then at the corner is equal to 180. That's 120 plus 60. This transfers inside, so that's going to be my starting moment on the beam is 180. And now you guys can see we have a triangle that we need to calculate to get this back to 0. So I'm just going to sketch it for now. I know the point here, and this is very important to understand, the shear force in this point is equal to 0. That means at that particular point, that's where you're going to get a maximum bending moment. So I know the moment is parabolic, and I know this point here is going to be the maximum because this is where the slope is 0. Okay, so very important concept to remember. Every time you have shear force equals to 0, you have the maximum of your bending moment diagram. But okay, now let's get some numbers in. So I'm trying to get this point here in black. So I'm going to get this area of this triangle, which for that I need this dimension here. So what can we do? We know we start at 6. We know the slope of this line here is the load. So the slope of the shear force diagram is equal to 12. So with this information, if we know we start at 6 and every meter we drop 12, then we know this is 0.5 meters. So that's pretty good. We can now get this area as 6 times 0.5 divided by 2. So that's 3 divided by 2 is 1.5. which then means this maximum moment here is 181.5. That's the maximum moment. And now, this final area, let me get rid of this slope as well. This final area should give me also 181.5. So the area of this triangle is 66 times, and now what's the entire length? Let's have a look. That's 6, so it's 66 times 5.5 divided by 2. And this is indeed equal to 181.5. So it's this area that allows me to get from this point here to 0. Okay? So that's my bending moment diagram. It's a little bit complicated to see, but it's 0 to 120, then to 180. Then the 180 gets transferred to the beam, passes by 181.5 after 0.5 meters, and then closes at 0. With all this information, I can now sketch my deflected shape, which is a lot easier to do once you have the bending moment diagram. So what I know now is I'm going to have the column bending towards the right. Then I'm going to have the 90-degree angle, and then the beam is going to be happy. The 90-degree angle is not very good there. Let's try one more time. And now our bending like this. And then finally we have 0 bending in our other column. So this obviously is very exaggerated, but the idea is still there. Okay? And again, remember, this bar has no bending. Okay? And the other one has bending. Now let's try to finalize this complicated problem using the same methods that we just did. So let's start with the reactions. So we can see that the horizontal reaction here is 40 because we have two loads of 20. And now let's say, for example, I want to get the moment here to calculate the reaction here. So I'm going to have 20 times 2, that's 40. Then 20 times 4, that's 80. So all of this together is 120. Then I also have 30 times 4, that's another 120. Then I have 10 times 2 times 1, so that's 10 times 2, 20, times 1 is another 20, all in the same direction. And finally I have another 20, that's this one, in the other direction. So I'm going to get rid of this 20 to compensate. So that means I have 240 rotating clockwise. This load is going to do counterclockwise, which is perfect. And now it's 240 divided by 6, which is 40. Now, if this one is 40, I know this one in total is 20, that one is 30, so this one here has to be 10. So we have vertical equilibrium in this structure. Okay, now we have the reactions. Let's go into the bending moment diagram and try our best to draw as much as we can. And if we figure out we can't do everything, we go to the shear force to help us with the diagram. So we know we start at 0, finish at 0. Now we know the shear force in the column, it's 0 at least in the beginning. So until here, until the 2 meters, we don't have any bending moment. Okay, we don't have shear force, so we can't have any bending moment. Then the load of 20 actually is going to start making it bend with tension on the left side. So now I know this has to go to the left with a triangle, and then the moment is 20 times 2, that's 40. That can go there, and that gives me my initial moment of 40. Now, if I go to the other column, this other column will have tension on the right side. So I know the moment here, it's going to be 40 times 4 is going to be 160. And now this 160 will be transferred here, plus or minus 20. So let's stop here a little bit and do a zoom on the node to try to figure out in which direction we need it. So I'm going to do the zoom here, down here. This is what I have. Then I have 160 that causes tension on the right, so it should be like this, which then would mean I would have 160 that has tension on the top. But on top of this, I have the 20 that does this. So this is not in equilibrium, which means to make this in equilibrium, I need this one to be 140. And now everything is fine. So I know this moment here is 140. Okay, finally, we could try to solve the beam straight away, but maybe I need the shear force diagram for that. So let's just do it very quickly. So I already know the shear force is 0 here, and then it goes to 20 in the rest of this bar. And then on the other bar, it has a constant shear force of 40, but we knew this already. But now let's look at the shear force on the top. So it starts at 10, and then we have a UDL of 10 in 2 meters. So it goes from 10 to 0 and then to minus 10. Okay, so that's the shear force there. Let me just move the 20 a little bit here. So then it goes to minus 10 there, stays constant for another 2 meters. Then the 30 bounces it down to minus 40. And then this stays constant until the minus 40 closes it. Okay, so now we need to figure out a way to calculate all these areas so we can close our bending moment diagram. So this first area here is 10 times 1 divided by 2. So this area here is just 5. This second area is going to be minus 5. So what we know is that we're going to go from 40 to 35 and then back to 40 because of this little area. So this is the parabola underneath the UDL, and it just goes from 40 to 35 and then back to 40. And then finally, we do have another area here, which is 10 times 2. So this area here is minus 20. And finally, this big area is minus 80, minus 40 times 2. So from 40, we're going to go to 60. So that's the moment after 2 meters is there, 60. And then I'm going to just make this a little bit bigger so the scale looks a little bit better. So from 60, when we add 80, it goes to 140. And then we did this part already. That's the 160. And that closes there at 0. And not an easy bending moment diagram, but makes sense because the problem looks complicated as well. But we figured it out. This is all adding up. We have slopes that are constant when we don't have UDL. When we have the UDL, then it becomes parabolic. So it looks pretty good. Now, final step is to do the deflected shape. I'm going to do it here in the corner. Here, we can say, okay, where do we have tension? Where do we have supports? So we know this point needs to stay here in the column. It's going to bend towards the right. Then we're going to have tension on top all across the beam. So that's actually not very difficult to sketch. Something that will look like that. And now what we have to do is something that bends towards the left, but then eventually stops bending and goes straight. So, okay, this drawing is not fantastic. Let's try to improve it a little bit. But the idea is there. So once that point here gives me the 90-degree angle, it bends. Okay, let's see if I can do this from the beginning. Like that. Then this will bend up, get here. Then this will bend to the left. And eventually, when we get halfway, when we get more or less halfway, we stop bending, and then it's just a straight line. Okay? And this, obviously, this point, and again, guys, this is very exaggerated displacements, right? We're talking about a sketch, but this is the way this is going to look. So this problem, despite being complicated, I hope it was a good learning object for you, and you learned something different today. You can find many of these problems online. There's plenty of other material on this, so just keep working on it, and I'm pretty sure you're going to be able to do this in the future very well. So thank you for watching, and have a nice day.